yesterday we have seen how to calculate the S parameter S based on incident radiation IT and tau alpha average by calculating. So, these two values, how to calculate the energy which is absorbed by or radiation which is absorbed by absorber plate. So, the maximum possible useful heat gain can be achieved when a collector is at the same temperature as that of the inlet fluid, right, where heat loss is minimized. So, in actual practice it is not possible. It is possible only when if we introduce a parameter called heat removal factor, right. So, this is ideal case in the sense. So, getting this one done, right, the maximum possible useful energy gain. So, this we reviewed in lecture 1 itself, right, based on thermodynamics law. You cannot convert the energy into 100% useful work, right. So, in actual operational setting, converting the useful heat gain, right, from the radiation received may not be possible, 100% possible. So, that effective useful energy heat gain is via heat exchange can be defined by the factor Fr, which is nothing but heat removal factor. So, this coefficient shows how much energy remains after heat losses to the surrounding due to collector and inlet temperature difference, right. So, this same formula you might have seen as a Qu as AP S minus UL AP TPM minus TA. This is plate mean temperature. So, we do not have plate mean temperature, but we need to analyze the system in terms of inlet temperature. So, that is what here it is said. It is a coefficient which shows how much energy remains after heat losses to the surroundings due to collector and inlet temperature difference, right. Therefore, the energy balance equation for the actual system can be written as follows. So, here we are introducing factor Fr AP S minus UL AP Fr TPM minus TA. So, if you define Fr, which is nothing but Qu upon AP S minus UL AP TFI minus TA. This is not PM, this is Fi. So, if the plate temperature is at fluid inlet temperature, so how much actual heat gain we get? So, that is defined by the factor heat removal factor. To define heat removal factor, again we need these parameters. One is plate effectiveness, which is nothing but phi. So, this is defined as tan H of m W minus D naught. So, this m is defined here again. So, this is overall heat loss coefficient. So, this is thermal conductivity of the plate material. This is thickness of the plate material, and this W is center to center distance, that is pitch of the fluid passage, and D naught is outer diameter of the tube. So, which is called plate effectiveness heat conducted through the plate to the fluid tube upon heat that would have been conducted if the thermal conductivity of the plate is infinite, was infinite. So, that means the conductivity is so high. So, without any resistance it directly reaches the working fluid. So, that is this parameter plate effectiveness. Another parameter is F dash, which is collector efficiency factor, collector efficiency factor, so which is equivalent to the ratio of actual useful heat gain rate per tube per unit length upon gain in the sense useful heat gain that would have been occurred if the absorber plate was at local fluid temperature, that is nothing but TF, local fluid temperature at that particular point of contact. So, that is nothing but F dash. So, here the problem is if you do not know Q a priori, then your FR, which is nothing but heat removal factor, can be defined using plate effectiveness and collector efficiency factor. Other than that, what we would require is area of the plate, absorber plate, that must be known, the mass flow rate of the fluid flow, that must be known. Then this is specific heat of the fluid, UL is heat loss coefficient, it is basically all our resistance, right. So, this is due to fluid flow, this is due to adhesive resistance. Right, this is heat transfer coefficient HF, 1 upon HF is inside the pipe, right. So, dI is multiplied, pi dI is multiplied. So, these are all basically a resistance, right. So, all this resistance 1 upon resistance is nothing but collector efficiency factor. So, FR here is a function of F dash, this F dash is again a function of phi, that is nothing but plate effectiveness. So, in that way one can calculate the QU, right. So, because what we said here is S we know by calculating IT, and UL heat loss coefficient we supposed to get it from correlations. So, we will see in detail how to do that, and inlet temperature we are known, the ambient temperature is we get it from environment. So, AP is known, then for constant FR and UL this heat gain can be calculated. So, after doing so, for example, this UL, right, what is UL? UL is overall heat loss coefficient. So, whether it is a constant value to be given, or if not how to calculate, right. So, this comes from the basic things AP into S, which is nothing but QU plus QL, right. So, QU is useful heat gain, QL is heat loss. So, this QL can be further written UL AP TPM minus TA. So, this overall heat loss can be divided into 3, QT, QB, QS. This is top loss coefficient UT, AP, TPM minus TA. QB is nothing but UB, AP, TPM minus TA, and this is US, AP, TPM minus TA. So, in that way AP, TPM minus TA is common for all the losses. So, in a way it can be written as the overall heat loss coefficient can be written as summation of top loss, bottom loss and side loss coefficient, right. So, here if you see these two equations, it is a basically QT upon AP. So, this is to calculate top loss coefficient, right. So, bottom loss, side loss we will see in successive slides. So, UT, how to calculate UT, right. So, if you combine here QT upon AP, which is nothing but UT into TPM minus TA, right. And same way you can calculate UB, US as well. So, first we are going to see this one. So, I need to calculate what are all the losses from plate to cover and cover to surrounding. So, that is what it basically says. So, this is between plate to cover and the second one is from cover to surroundings, right. So, to write this equation there are certain assumptions we take for this thermal analysis, whole thermal analysis done at under steady state and one dimensional. So, we consider them the plates, right. This is your cover and this is your absorber plate. So, we consider them as a infinite parallel surfaces. Flow of heat is one dimensional and steady. The third is del T across plate thickness is negligible. Interaction between incoming radiation absorbed by covers and outgoing radiation is also negligible. And outgoing radiation is only long wave radiation. Radiation is long wave radiation. So, by considering these assumptions, so we are going to balance these two equation. So, that is nothing but this is absorber plate. So, this is cover. So, from absorber to cover there are two components, one is convection losses, another one is re-radiation losses. The same way from cover to atmosphere as well. So, the first component of these two equation talks about convection losses. So, this is heat transfer coefficient between plate and cover system. So, this can be obtained using Nusselt number correlations, using Nusselt number which is nothing but H upon K, which is heat transfer coefficient upon thermal conductivity multiplied with characteristic dimension of the system. So, if you know correlations, if you can calculate NU, then you can get H from there. The same way you can use correlations to calculate the air heat transfer coefficient. So, this is plate mean temperature minus cover temperature minus atmosphere temperature. So, this is a convection loss and here it is re-radiation loss. So, which involves plate mean temperature, sigma is nothing but Stefan-Boltzmann constant, and cover temperature. This is plate emissivity, cover emissivity. The same here T sky temperature, which is normally taken as TA minus 6. This is ambient temperature. This is plate emissivity and sigma is again Stefan-Boltzmann constant. So, by comparing these two, right, your plate mean temperature TPM would be fixed. So, for that before, if you know this, then you can calculate UT, or directly you can also fix UT using again correlations. There are correlations which gives you directly how to calculate top loss coefficient. So, this iteration procedure we will see in detail while doing problems, there you will understand better. So, how to use these three equation without UL. I do not have UL right now, right. So, without UL, so there we are going to assume UL and calculate these parameters. After calculating these parameters, you will find out TPM, which is nothing but plate mean temperature. So, that plate mean temperature you would get by assuming UL, right. Then how to correct that further, and here again one more unknown parameter is there, which is nothing but Tc, right. So, out of these two equations we would get Tpm and Tc. So, this is again the value we got by assuming some UL, right, and we do further iterations to correct Tpm value and Tc value accordingly, because we used Tpm and getting Tc, right. So, that we can see in problem section how to do that. Otherwise, one can directly use UT, and UL is for example, if you write it in terms of B, QB upon AP, which is nothing but UB Tpm minus Ta. UB can be directly calculated as Ki insulation upon delta B, right. And another parameter is Qs upon AP, which is nothing but Us Tpm minus Ta. So, Us can be written as L1 plus L2 into L3 into Ki upon delta S. L1, L2. So, this L1, L2 are the collector dimensions, length and width, and L3 is nothing but the height of the casing. So, these formulas everything is given in Professor Suhatme and Noack book, that is the main reference book of this particular course. You can refer over there. So, this one can directly calculate using correlations and the formula directly UL, and then from UL you can get plate mean temperature, and plate mean temperature, using that you can also calculate the collector temperature, but if not, then one has to do iterations. So, the next one is a performance test. When you are getting a new collector, so how to test their performance, right. So, that is what basically we are going to see here. So, the theoretical models and calculations can be done, that is what we have discussed till now, how to get useful heat gain Qu, right, UL, Fr, so that I can directly calculate the instantaneous efficiency. So, the theoretical models and calculations can be done, however, it can be checked by practice by performing collector test, right. So, whatever numerical modeling and simulation you do, so that has to be finally validated with the experimental results, or if you are designing a new collector, that test has to be performed to compare with the existing collectors and how much performance improvement you are able to bring in the new system. So, for that you are supposed to do expose the system to solar radiation and run the fluid through it and measure the inlet outlet temperature along with the flow rate. So, Tfi, Tf0 and mass flow rate. Then calculate the useful heat energy gain from the experimental data. So, mass flow rate we measured, T out, T in we measured, this is the fluid Cp which is the average value of what is the Cp at Tfi, normally we take, right. So, this is the normal calculation we follow. So, average Cp and calculate Qu. In addition, the incident radiation of the collector IT, this also can be calculated. We have read, right, the pyranometer, using instrument we can directly read the particular time or particular day what is the incident radiation, and ambient temperature also can be recorded, so that we express Qu in terms of AP Frs minus UL T in minus Ta. So, here we used only the inlet fluid temperature, that is why we have taken Fr, right. So, if you think little bit, so Qu I will divide it by IT AC, which is nothing but instantaneous efficiency. So, this side also if you divide AP upon AC, Fr I will keep it. So, here S I can write it as IT tau alpha average upon one more IT is here minus UL IT upon IT. So, this one should not get confused, T in minus Ta. Okay. This IT get cancel. So, instantaneous efficiency, which is nothing but QU upon ITAC, which is nothing but AP upon AC. This is plate area, collector area, into FR, tau alpha average minus UL upon IT into T in minus TA. If you want to write it, F R AP AC tau alpha average minus UL IT T in minus TA FR AP AC, right, which is equivalent to y equal to mx plus c form, right. If you have a plate area as well as the collector area same, or one can calculate instantaneous efficiency based on AP as well, right. So, if both areas are same, then this must be going, then what you would get is eta I is nothing but FR tau alpha average minus UL FR into TI minus TA upon IT. If you plot T in minus TA upon IT versus eta I, right. So, what you would get, UL FR as a slope, for example, this is the line with the negative slope of UL FR, and your intercept would be FR tau alpha average. So, one can compare the performance of new collector with the existing collector and always come up with the performance curve, right. This has to be done for closed system. For example, so you have a flat plate collector or new design whatever you come up with. So, here you may use heat exchanger with the cooling cold water. This is heat exchanger, and you can use one more storage tank with heater facility, right. So, this has to be pumped, go to flow meter and go to FPC. Flow meter you measure m dot. So, here you measure with temperature sensor TF, TF naught, and TA, IT you use pyronometer and temperature measurement of the ambient. So, this is this particular arrangement. Even pump you can also use one bypass valve to adjust the flow rate. So, these are all done the auxiliary arrangements to make sure the mass flow rate and TF is whatever you wanted. So, normally this test has to be performed for 4 timings. So, normally we say solar noon is the maximum radiation. So, before that to probably 11 and 11:30 lat local apparent time. The same thing here 12:30 and 13 hour of lat. So, at least for 4 various inlet temperature, and by fixing one particular mass flow rate, right. At least 16 measurements to be done for one particular mass flow rate value. So, when doing so we supposed to maintain under clear sky, right. This test has to be performed under clear sky. The IT should be around 700 watt per meter square, and the wind velocity should be around 2 to 5 meter per second, and the mass flow rate should be at least 0.2 kg per second. So, this we need to ensure, and also there are some experimental errors, right. So, how much it is possible for IT plus or minus 50 watt per meter squared error is allowed. For getting TFI we are measuring TFI and TFIR. So, there plus or minus 0.1 degree is allowed, and the del T should be about plus or minus 0.1 degree, and mass flow rate 1% is allowed, and ambient temperature around 1 degree centigrade error is allowed. So, by keeping this error values in mind and by keeping at least this around IT V infinity m dot, so this performance test has to be performed. So, this is based on the Indian standard value 12933. So, this kind of performance test, and this is closed loop. So, one has to perform parallelly the open loop as well as solar simulator. To do solar simulator, that is what we learnt, right. So, how to calculate QU and eta I using formulae and correlations, and then compare closed loop performance test, open loop performance test, and performance test performed by solar simulator. So, that is all about thermal analysis. Then next is what are all the advantage of flat plate collector. So, it absorb direct, diffuse, reflected components of radiation, simple in design, there are no moving parts, and the tilt and orientation is fixed. So, no need for tracking the sun, easy to make and low in cost, have comparatively low maintenance cost and long life, operate comparatively at high efficiency with less labor and complexity. So, that is where advantage of getting comparatively high efficiency for less investment. Okay. So, summary, FPC comes in various shapes, size, materials and configurations. As a representative case for understanding the energy balance and system performance, we thoroughly done liquid FPC, right, how to do theoretical calculations as well as how to get experimental parameters, and absorbing as much solar radiation as possible using black absorptive surfaces, minimizing losses to the surrounding environment as much as possible using glazing surfaces, insulation and vacuum tubes, using various technologies with the trade-off among level of performance and material and manufacturing costs. We would say flat plate collector would be the best to collect solar radiation for low temperature applications. Then we will see certain modifications and solar air heater and their applications in the next lecture. Thank you.